Section: Introduction. In this section, we discuss the introduction of large language models, LLMs, and their impact on natural language processing, NLP. While these models have greatly advanced the field, multilingual LLMs are still quite limited, especially in the open source area, where the demand for diverse language support is not being met. Existing open source multilingual LLMs, like Bloom, GLM-4, and Qwen 2.5, mainly focus on languages with abundant training resources, typically those from developed countries, such as French, Arabic, and German. Unfortunately, languages from less developed regions, like Hindi, Bengali, and Urdu, which have millions of speakers, often receive less attention. To address this issue and make LLMs more accessible globally, we introduce Babel, a new open-source multilingual LLM designed to support over 90% of the world's speakers. We focus on the top 25 languages by speaker count, including English, Chinese, Hindi, Spanish, Arabic, and others. Many of these languages, despite their large number of speakers, have been overlooked by current open-source multilingual LLMs. Recognizing the challenge of limited high-quality training data for these languages, we prioritize optimizing our data cleaning process to ensure the best data quality. We gather data from various sources and use an LLM-based quality classifier to curate clean, high-quality content for training. Instead of traditional pre-training methods, we enhance Babel's capabilities by expanding its model size through layer extension, which adds new layers that mirror the original architecture. We present two versions of Babel, Babel 9b, which is efficient for multilingual inference and fine-tuning, and Babel 83b, which sets a new standard for open multilingual LLMs. Our evaluations on multilingual datasets show that Babel outperforms other open LLMs of similar size. We also utilize open-source supervised fine-tuning datasets, like WildChat and Everything Instruct Multilingual, to create a training pool of 1 million conversations without generating extra training data. This pool is used to train Babel 9b base and Babel 83b base, demonstrating strong task-solving abilities even with publicly available fine-tuning data. Notably, Babel 9b chat achieves top performance among 10B-sized LLMs, while Babel 83b chat sets a new benchmark for open LLMs, performing comparably to leading commercial models like GPT-4o on certain tasks. In terms of supported languages, we note that while current LLMs like GLM-4 and Qwen 2.5 are expanding their support for non-English languages, they still focus on those with extensive training data from developed countries. In contrast, languages from less developed countries, such as Hindi, Bengali, and Urdu, receive less focus despite their large speaker populations. To ensure broader accessibility, we selected 25 languages based on the number of speakers, ultimately covering around 7 billion speakers globally, which is over 90% of the world's population. For data preparation, we have expanded our data sources by incorporating valuable information from resources like Wikipedia, textbooks, journalistic content from CC News, web-based corpora like Cultura X, and the MADLAD 400 dataset. Section Summary. In this section, we highlight the introduction of Babel, an open-source multilingual large language model designed to support over 90% of the world's population by focusing on the top 25 languages, many of which are often neglected in existing models. We emphasize our efforts in optimizing data quality through a diverse collection process and innovative model expansion techniques, resulting in Babel 9b and Babel 83b, which demonstrates superior performance compared to similar-sized open LLMs. Section: LLMs-based data cleaning and processing. In this section, we focus on data cleaning and processing using LLMs. Given the limited high-quality training data for many languages, we prioritize optimizing our data cleaning pipeline to achieve the best data quality. Here are the steps we follow. First, we normalize the data by applying specific rules to filter out low-quality entries, such as documents with fewer than 100 characters or those with more than 30% digits. Next, we develop a quality classifier using the QWEN 2.5 to 0.5b instruct model. We combine strong model-based labeling with expert linguistic refinement to create our training dataset. We use the LLM as a judge method, where we prompt GPT-4o to evaluate and score potential training data on various aspects. Linguistic experts then review these scores to ensure we select only high-quality data for training. We also deduplicate our data by identifying and removing duplicate documents through hashing, pairing, graph construction, and recording duplicates for removal. To enhance our model's performance, we expand its parameters. We do this by adding new layers that mirror the original structure, ensuring that critical components like attention heads and embeddings remain unaffected. We focus on extending layers in the latter half of the model, exploring different positions for adding layers and various methods for initializing new parameters. We test inserting layers between existing ones or appending them at the end. For initialization, we consider duplicating original parameters, starting with zeros, or adding noise. We choose the best methods based on initial performance, aiming for minimal disruption. We conduct an ablation analysis using Qwen 2.5-72b base as our backbone model, evaluating performance on the MMMLU. We look at two main factors: the position of layer insertion and the initialization method. Our results show that appending new layers significantly reduces performance, while inserting them within the existing structure causes only minor degradation. Duplicating layers without noise yields the best results, maintaining original feature integrity. However, adding high mean Gaussian noise negatively impacts performance. Initializing with zeros preserves original performance but degrades after training. Therefore, we choose to initialize with Gaussian noise at a mean of 0.0001 to balance stability and adaptability. For model architecture, we select two sizes, around 10 billion and 80 billion parameters. Using Qwen 2.5b7b and Qwen 2.5-72b, we apply our layer extension method to initialize Babel 9b and Babel 83b, inserting layers in the second half of the model. In Stage 1, we recognize that modifying parameters can disrupt the collaboration of well-trained parameters, leading to a drop in Babel's initial performance compared to the original model. Thus, we require a large and diverse training corpus for recovery. We sample a balanced corpus for each language from the pre-training data, though achieving perfect balance is challenging due to limited resources for some languages. To speed up recovery, we combine English and Chinese training corpora, using well-curated datasets like Red Pajama and Proofpile 2 for English and Yai 2 for Chinese. In Stage 2, we focus on enhancing multilingual capabilities, especially for languages that previous models have overlooked. We increase the representation of low-resource languages in the pre-training corpus and continue training the model, also boosting the proportion of textbooks in the training data, as they are more effective for LLMs to learn new knowledge. Section Summary. In this section, we outline our optimized data cleaning pipeline for training language models, emphasizing normalization, a quality classifier using LLMs, and deduplication to ensure high data quality. We also describe our model extension strategy, which involves adding layers to enhance performance while minimizing disruption, and detail our two-stage training process focused on recovery and continuous improvement for low-resource languages. Section: Evaluations. In this section, we evaluate Babel against similar-sized open-source and commercial multilingual large language models, LLMs, across a wide range of multilingual tasks. For our dataset, we use various multilingual tasks categorized as follows. 1. World Knowledge, which includes MMMLU, a human-translated version available in 14 languages, and M3 Exam, featuring real exam questions from different countries and educational levels. For languages not included, we use Google Translate for translations. 2. Reasoning tasks include MGSM and XCOPA. 3. Understanding tasks involve XNLI. And 4. Translation tasks are represented by Floor 200. In our benchmark, we compare Babel 9b with several models, including GLM 4-9B, Gemma 2-9B, Mistral 12B, Llama 3.1-8B, and Qwen 2.5-7B, based on their release dates. We also compare Babel 83B with Llama 3.1-70B and Qwen 2.5-72B. For evaluation, we apply few-shot prompting methods across all datasets and models. We measure accuracy for all datasets except Floor 200, where we use the CHRF++ score for translations between each language and English. Our main results show that Babel 9B base outperforms other 10B size models, achieving an average score of 63.4, which is 3.9 points higher than the next best, Gemma 2-9B base. Babel 9B base excels in XCOPA, MGSM, XNLI, and Flores 200, showcasing its strong multilingual reasoning, understanding, and translation skills. While Gemma 2-9B base performs well on MMMLU and M3 exam, Babel 9B base maintains consistent strength across all benchmarks. For Babel 83B base, we find it achieves the highest overall performance among the evaluated models, with an average score of 73.2, surpassing Qwen 2.5-72B by 3.4 points. It also leads in MMMLU, M3 exam, XCOPA, XNLI, and Flores 200, reinforcing its capabilities in multilingual tasks. To analyze Babel's performance across languages, we categorize them into high resource and low resource based on their availability of public training data. High resource languages include English, Chinese, and others with scores above 1, while low resource languages like Hindi and Arabic have scores below 1. We observe that low resource languages have been less explored by previous multilingual LLMs. Our analysis shows that Babel 9B base significantly outperforms Qwen 2.5-7B base on low resource languages. In contrast, it also performs better than Gemma 2-9B base on high resource languages. Overall, Babel 9B base achieves the highest average performance and balances well between high resource and low resource languages. Section Summary. In this section, we evaluate Babel against various multilingual LLMs using a range of tasks, including world knowledge, reasoning, understanding, and translation. Our results show that both Babel 9B and Babel 83B outperform their competitors in overall performance and across different language resources, demonstrating strong capabilities in multilingual understanding and reasoning. Section: SFT Data. In this section, we focus on the SFT data. We primarily use open-source multilingual SFT training datasets and translated SFT training data. Specifically, we utilize Wild Chat, which includes 1 million conversations between users and ChatGPT, totaling over 2.5 million interaction turns. We also incorporate Everything Instruct Multilingual, a large dataset formatted for Alpaca Instruct that covers a wide range of topics. We explore two methods for creating an SFT data pool with 400,000 conversations, one in English only and the other in multiple languages. Our comparison shows that while the English SFT data improves the model's ability to follow instructions, the multilingual SFT data significantly enhances overall performance. As a result, we create a larger multilingual SFT data pool, which consists of about 1 million multi-turn conversations. We present a figure that illustrates the distribution of SFT data across various languages, excluding English and Chinese for clarity. English makes up 40% of the total SFT training data, while Chinese accounts for 10%. During SFT training, we pack conversations together for efficiency, adhering to a maximum token limit of 4,096. We set the learning rate to 4 millionths and apply a warm-up ratio of 0.1. Our main results indicate that Babel 9B Chat achieves the highest average score of 67.5, outperforming Gemma 2-9B Instruct, which scores 65.7, and other models. Babel 9B Chat leads in 5 out of 6 benchmarks, excelling in XCOPA, MGSM, XNLI, and Florus 200, showcasing strong multilingual reasoning and problem-solving skills. Although Gemma 2-9b Instruct slightly edges it out on M3 exam, Babel 9b Chat remains consistently strong across tasks. We also find that Babel 83b Chat achieves the highest average performance of 74.4 among open multilingual LLMs, closely following GPT-4o at 75.1, and surpassing Qwen 2.5-72b Instruct and Llama 3.1-70b Instruct. With top scores in XCOPA and XNLI, Babel 83b Chat is the closest open multilingual LLM to the best commercial option, demonstrating impressive multilingual capabilities. Importantly, these results are achieved using only publicly available datasets, highlighting the strong foundational performance of our Babel base models. We believe that adding more SFT data from various types, domains, and formats, along with additional alignment data and preference tuning, will further improve the chat version beyond its current capabilities.